Alrighty everyone, welcome back to a second video topic. Here we're going to be discussing bonding, IMFs, and then we're going to get a bit into general gases and deviations from ideal behavior, that kind of stuff. Again, all this stuff with bondings and IMFs is going to be the basis for your explanation for the majority of questions you will be asked in the FRQs. Not necessarily the answer to everything, but the reasoning and the general understanding as to why things happen the way that they do. So first, let's get into bonding. What is a bond, and how can you recognize when you have a bond compared to an IMF? A bond is going to be, for starters, inside a molecule. And IMFs are going to be outside molecules. The second distinction between these two is that bonds deal directly with electrons, so some interaction between an electron, be it a transfer, sharing, or whatever. IMFs has no electron interaction. There will be an interaction between the regions of space that are either positively or negatively charged, but no discrete transfer or sharing of any given electron. Now, that being said, what kinds of bonds do we actually have? We have covalent bonds, polar covalent, ionic, and metallic. So covalent bonds. Covalent bonds are those which have equal sharing, equal electronegativity values, or roughly equal electronegativity values. A covalent bond would be something like a carbon-carbon bond. In a covalent bond, in every bond you will have a certain region of space between two electrons. A covalent bond is the one such that in here, in the center, you will find the majority of the electrons. Say, I can find the electrons 80% of the time here. Off to the sides, 10% of the time, you will find them here. This idea where the electrons are going to be equally shared between these two things is a covalent bond. Now, again, these are rough numbers, but there's two things to note. Most of the time, in a covalent bond, they're going to be pretty much in the center. Second thing to note, which is going to be very important later on when we talk about IMFs, they can be found off to one side. You know, a covalent bond is represented by two electrons. If you were to freeze this and look at these two electrons, most of the time it's going to be right here. However, sometimes you might find it off to the side. So that's the essence of a covalent bond. Now, what about a polar covalent bond? A polar covalent bond might be something where we see a carbon bound with oxygen. And these are all single bonds, by the way. Again, same region of space, but instead of having it 80% the center and then 10%, 10%, we might see a distribution of, on the right half, 70% of the time, you find the electron there, and on the left hand, 30% of the time, you find the electron there. So clearly, most of the time, the electron is going to want to stay towards oxygen. Not always, but a good deal of the time. And again, always two electrons. That's how these bonds are represented. So oxygen, having a higher electronegativity value, will want to pull the electrons more strongly towards it. Then the third one is going to be an ionic bond, something like sodium and chlorine. In that region of space, you will have the electron off to one side most of the time. So 90% of the time you might find it right next to chlorine, and then maybe only 10% of the time around sodium. Here we see that as more as of a discrete transfer of electrons. In this case, it is one electron versus here in a covalent bond having two electrons. So covalent bond always refers to two electrons in polar covalent bond. Ionic is really always a transfer of one electron. If you have something like MgCl2, obviously there's two electrons being transferred, but one coming from each chlorine. And something with a charge of +2 and -2 would have 2 electrons also, but in one bond. So it really, in reality, this number will tend to vary. I wouldn't feel good saying it wouldn't feel right saying it's either 1 electron, 2 electrons all the time. Then metallic is a completely separate case. So let's talk about that a bit more. So what is a metallic bond? When you think of metallic bond, the word that needs to come to mind is a sea of electrons. That is the term you will use to describe this if you're ever asked to describe it, although it really tends to show up only for multiple choice questions. What kind of questions you're going to be seeing are pretty much always just classifying it. A metallic bond is going to be one where we're dealing specifically within transition metals. So let's do chromium or something. So you have a bunch of chromium atoms, and they exist as a big unit put together of just a certain ratio of them. Electrons in this capacity have the ability to flow. They can conduce and move around. That's why it's referred to as a sea of electrons. This will not necessarily be the case for ions, but in a metallic bond, ions, referring to ionic bonds specifically, in a metallic bond, that is exactly the case. There's two kinds of variations to this. When we mess around with this, we get something called alloys. First, you have an interstitial alloy, and then we have a substitutional alloy. The interstitial alloy is the one where you will take an atom of a much smaller size and it will be placed in between the space of the other atoms. Imagine that we're looking at a whole bunch of gold and we put one zinc atom. Zinc is in the 4th energy level, gold is in the 6th. So if the zinc is going to be much smaller, it might be able to occupy this space in between. A substitutional alloy is when you take that same metal, except instead of putting any given atom inside the space where those atoms are, you replace it with a slightly bigger or a slightly smaller atom and have that take its place. This might be copper and zinc, for instance, which are right next to each other on the periodic table, or chromium and manganese, again right next to each other. So they have to have comparable sizes. Why does this happen? Most of the time we want to mess around with its malleability. We want to mess around with conductivity. Obviously at this point you would have an increased molar mass as well, and so forth. Cool, moving on. Let's talk a bit more about the different kinds of bonds that you're going to be seeing within a covalent or polar covalent bond. Imagine a carbon-carbon bond. This is going to be a single bond. Oxygen is typically double bounded, and nitrogen is triple bounded. If we were to take this, imagine it as looking at a piece of rope. So I have a fixed amount of rope. We're going to say we have that fixed amount. To make a double bond, take your rope and then split it in half. What do you expect to happen? The rope length would obviously have to shorten, right? For a triple bond, take that same piece of rope and split it into thirds. Again, it will shorten. So here we have the longest piece. Here we have the shortest piece. What else is going to happen? The strength of that rope. If I have one long rope, one piece of rope, it's going to be the weakest. Versus that same piece of rope split into 3 sections at 3 different attachments, it's going to be the strongest. So triple bonds tend to be the shortest and the strongest, with a single bond being the longest and the weakest. What else do you have? You have different kinds of bonds showing up here. Referring specifically to sigma bonds, denoted as such, and pi bonds. You don't have to understand what this means. This comes from ideas in MO theory, molecular orbital theory. If you were taught anything in your class about MO theory, honestly, especially by this point in the game, completely forget about it. You will not get a single question on MO theory showing up in this exam. The only thing you have to know about sigma, and the only thing you have to know in reference to that is sigma bonds, pi bonds, and hybridization. We're going to cover those three exactly right now. Sigma and pi refer to the different numbering, quote unquote, of the bonds showing up. The first bond is always going to be a sigma bond. And when I mean first, I'm referencing sigma to single, double, and triple. Every other bond is going to be a pi bond. I'm going to denote single bonds in yellow right now, so carbon, carbon, oxygen, oxygen, nitrogen, nitrogen, and then I'll draw the pi bonds in a different color. So here, how many sigma do I have? And here, how many pi do I have? Sigma, one sigma bond, one sigma bond, one sigma bond. If you have a bond, a covalent bond, the minimum number of sigma bonds is 1 if it's bounded, and the maximum number of sigma bonds is 1. Everything else is going to be a pi bond. This case, 0 pi bonds. This case, 1 pi bond. This case, 2 pi bonds. That's it. That's all you need to remember for this. The other topic that tends to cause a lot of confusion is hybridization. So a CH4 molecule. CH4 looks as follows. Your questions will be worded as such. Find the hybridization of a central carbon atom in the methane molecule. We look at the carbon, it's obviously this guy. We have to count the number of electron domains. What is an electron domain? A space that holds electrons. A single bond will count as 1 electron domain. So let's do electron types. So, and by types I mean just bonds, either single lone pairs or whatever we're talking about. And then here we're going to do domain number, domains. All of these are just going to be 1. So a single bond is 1 electron domain. A double bond is 1 electron domain. A triple bond is 1 electron domain. A single electron is 1 electron domain, and a lone pair is also seen as 1 electron domain. All these things count as 1. So if you have a double bond, you don't count it as 2 domains. You count it as 1. The number of total domains is going to tell you exactly what your hybridization is. Understand, in reality, this really has very, very little to do with MO theory. And when I talk about MO theory, if you've covered that, I'm talking about all the really weird shapes that you guys talked about with hybridization. So not the Vesper stuff, but the region where you have a bond like this, and then other areas of space circling it, and then when you have another atom comes into this, it makes the region all messed up and it takes a very strange shapes. You don't need to know that for this class. Let's count the number of domains around the central atom in a methane molecule. We have 1 right here, 2, 3, 4. What do you do with this information? The answer for any hybridization question is going to take the following shape. Your answer is either going to be S, incredibly rarely, really never, SP, SP2, SP3, SP3D, and so forth. So the question that asks, what is the hybridization of the central atom in any given molecule? These are going to be your answers. S corresponds to 1, SP to 2, SP2 to 3, SP3 to 4, SP3D to 5. Why is that the case? Imagine I put a little 1 here. 1, 1. 1 plus 1 is 2. 1 plus 2 is 3. 1 plus 3 is 4. 1 plus 3 plus 1 is 5. 4 electron domains. This carbon atom will have a hybridization of sp3. Let's do a couple more examples. So let's do CO2. We'll do BF3, and we'll do CO3. CO2 looks as follows, right? CO3 has resonance. If you don't recall what that is, we'll talk about it in a little bit. Different structure shows up. I think the carbon atom has a charge of -1, -2. I can't recall at the moment. -2. And then BF3 is something called electron deficiency, which again, we're going to talk about that later on. Main thing is, these is how they look. This is how they look. And let's also do N2 actually. We'll do them here. N2, triple bounded. Compare on each side. How many electron domains here? 1, 2. 2 electron domains corresponds to sp. What about over here? 1, 2, 3. 3 domains, that is sp2. Over here, 1, 2, 3. 3 domains, sp2 again. Things to note. Double bonds counts as 1. Double bonds and single bonds and resonance, again, they all count as 1. Only single bonds, they count as 1. Here, which one would be the central atom? Doesn't matter. They're both the central atom, just way of looking at it. So we're going to consider this nitrogen to the left-hand side. This is the first electron domain, and the second one is this lone pair. I have 2 electron domains here, so it is again hybridization of the central atom in a nitrogen molecule is sp. That's all the hybridization stuff you're going to be asked. By now, you should have seen graphs that look something like this. This is a graph that covers topics in internuclear distance. So on the x-axis, we're going to have internuclear distance. On the y-axis, we're going to have energy. As you increase in energy, there's some relation with internuclear distance. Obviously not linear. Sometimes it decreases, sometimes it increases, and so forth. Let's see what happens. How do you make something stable? The most stable configuration is always the one with the least amount of energy. So you can expect this section to be the most stable. If we're talking about an HH bond, here is the actual HH molecule and where it would want to exist at this point. What about all the other points? Over here, they're much too far apart from each other. This is not going to happen. And over here, they've become much too close to each other. This won't happen either. There is an ideal distance between the two. What else are you going to see? You're going to see a 0 right around here. This side is going to be negative, and this side is going to be positive. So, what does that tell you? This is asymptotic. The further away they get, they have to approach 0 because there's no energy, there's no attractive force between the two. Here, there's an attractive force pulling them together, but by this point, they got way too close, like too close such that the nucleuses are almost within contact and they're within each other and they can feel that positive force. So they're going to want to repel, and this configuration is going to have way too much energy. It's not something stable. You want the lowest amount of energy, and lowest means most negative. If you have some energy state of -3 versus an energy state of 0, the -3 one is the preferable state. This is all just a reference frame. Our reference frame is we're defining a state of 0, as the one that's infinitely far away from each other, right? That obviously isn't going to have any energy. Awesome. Moving on. So I briefly mentioned resonance. We're not going to talk about Lewis structures themselves and formal charges. There's tons of videos out on that, and that's a really super complicated topic. I don't want to get into that. It's not a complicated topic. So moving on, let's discuss resonance a bit more. With regards to Lewis structures and formal charges, I'm not going to discuss that because there's already tons of videos on that, and I do want to focus more on AP specific things. Not that it's not on the AP exam, you definitely will see that, but you already have tons of materials. Just Google, look up on YouTube, you'll find a lot of material on those specific things. But let's discuss the idea of resonance itself. Resonance. So what does resonance mean? If you do the formal charges for a carbonate molecule, carbonate ion, you'll see that the best configuration is as follows. I have one double bond and single bonds on each side. This is going to be in brackets. And you get a 2- charge here. And then you have little arrows off to the side. Things to note. These arrows, this means that you are in a state that is in between all the different states you're going to see. Resonance is a way for us to draw awkward bond angles. It does not mean we're switching back and forth between all of the states. It is one state in between as a combination of all the states that are being drawn. Second thing to note, you absolutely cannot miss out this number right here, that 2- or whatever it ends up being in your specific case. If you don't put it, you will likely lose all the points for that specific question, especially in FRQs. So make sure you don't forget it. And they always carry brackets as well. Then you just move around the one that gets double bonded, because these are all 3 different oxygens, right? There are 3 oxygens in one carbonate molecule. I'll single bond these and double bond here. So what would be the bond order? What is the average bond length of a carbon-oxygen bond in the carbonate molecule? Here, I have a double bond plus a single bond plus a single bond. How many bonds do I have in, how many regions where it's bounded do I have in total? 3. So what's my average bond length? 4 divided by 3, 1.33. Same thing here, same thing here. Resonance is a way for us to draw the structure that shows an average bond length of this case in the carbonate molecule, 1.33. The next 2 things that we're going to discuss are going to be incomplete octets and an expanded octet. So you know the octet rule is the one that says typically you want a molecule or any given atom to have 8 electrons in its valence. That tends to be a very stable configuration. It's not always going to be the case, but most of the time that is a very good answer. That's how we judge why most molecules tend to be the way they are. But that's not always the case. Sometimes there will exist molecules that are happy not having 8 electrons in its valence. Let's look at an incomplete octet. Incomplete octets are also known as electron deficiency, because I do not have enough electrons. The absolutely most common case of that is boron trifluoride. Boron, if you were to draw a full Lewis structure, you'll see that I have boron has 3 electrons in its valence, and fluorine has 7. So in total, 3 plus 3 times 7, we have 24 electrons. 1, 2, 3, 4, 5, 6. Each bond represents 2 electrons, so that one has 6 electrons. And let's do the lone pairs. 7, 8, 9, 10, 11, 12, 13, 14, 19, 20, 21, 22, 23, 24. So I have 24 electrons in that case. But what about this boron? How many electrons are around that boron? It's only 6 electrons. It just so happens that in this case, boron tends to be happy having an incomplete octet. It is by large the most common example for having an incomplete octet, or that state of electron deficiency, and this is the most common molecule you'll see. If you do the formal charges for this particular molecule, you'll see that the most stable configuration does end up being this. Aside from that, you can never double bond fluorine. Fluorine just really, unless it's an exceptionally rare case, it really does not want to be double bonded. Reason being, it only needs one extra electron, so one single covalent bond, in order to make sure it has the octet rule fulfilled. And fluorine tends to overpower everything because it does have an incredibly high electronegativity value. So what about the more interesting one? The expanded octet. Very common example would be PCl5. Phosphorus, pentachloride. So I'm going to do 5 chlorines around it, just to have the dots completion up here. I don't recall the exact number of electrons, but it really doesn't matter. This is the, if you want to check it, go ahead. This is the structure that phosphorus pentachloride is going to take up. But what do you notice? Right here, I've got in total 5 bonds, 2 electrons each, 10 electrons. I have expanded the octet for phosphorus. I don't have 8 electrons. Instead, in this case, I actually have 10 electrons around the phosphorus. Can you do this with a nitrogen atom, per se? If we tried to make out nitrogen pentachloride, which is only 1 above phosphorus, so as far as the actual molecule, it does seem to make a bit of sense as to that actually happening. So it would look something like this. And again, you would see 10 electrons here, same number of electrons in the valence, right? But what does nitrogen have access to? Nitrogen is in the second energy level. The second energy level only has S subshells and P subshells. The absolute max number of electrons he could hold is 8. So this specific structure could never exist. He can't hold 10 electrons. He doesn't have enough space. Versus phosphorus, on the other hand, third energy level. So he has access to S, P, and D. And that's what lets you expand the octet. You can only expand the octet for any given atom once it is in the third energy level and below. So this NCl5 does not exist. We're going to skip over VSEPR theory because that is something that it's covered incredibly frequently, and you can look up any video easily and find that on YouTube. The thing about VSEPR theory is you only need to memorize the shapes and angles that correspond to S, SP, SP2, and SP3. So SP3D, things like octahedron, all those kinds of shapes, you don't necessarily need to worry about. That being said, let's go ahead and move on to IMFs. So we already know that IMFs, they do not have any discrete interactions with electrons, not necessarily transfer or sharing, just any given interaction, and they occur outside of molecules. IMFs happen because of these things called polarities. There are charges and these weird forces that act in a molecule. If I have a region of space and I put an electron here, off to the left side of that space, this left side now gains a partial negative charge. In reference to the rest of my space, and let's imagine this is a vacuum for a second, this is negative. What about this side of the space? That ends up being positive. By reference, that lack of an electron made this section positive. Polarity describes that ability of any given, that ability to show and have this quality of some section having a negative charge and some section having a positive charge. With regards to molecular polarity for actual molecules, let's talk about H2O. H2O looks as follows. Oxygen, we know, is incredibly electronegative. These electrons are all going to want to spend most of their time around that oxygen, and on top of that, it has 2 lone pairs. So oxygen will have a partial negative charge on the oxygen side of the water molecule, and partial positive charges along the hydrogen sides. This is a molecular polarity. If you wanted to draw an arrow showing all of this, you put the positive side right here by doing this to the arrow and point it towards the negative direction. There is a vector for this specific water molecule showing that this area tends to be positive and this area tends to be negative. So why does this matter? This matters because that is the basis of how IMFs function. So we have a bunch of different kinds of IMFs. We've got LDS, London dispersion forces. We've got dipole-dipole. And then we've got H bonds. There are also ion dipole and a couple others, but these are the three main ones. Effectively, they function exactly the same way, except one has an ion. So you might be talking about like sodium instead of carbon or something. Now, first thing to note, before we even start discussing what each of these are, there's a word right here. H bonds, hydrogen bonds. A hydrogen bond is not a bond in the classical sense. It's a misnomer of sorts. It really shouldn't be labeled that way. If anything, you should call it H-IMFs, hydrogen IMFs. Or this is just what was chosen and what we have to deal with. A hydrogen bond is not a bond. Please remember that. A hydrogen bond is actually an IMF. Now, let's start the discussion with dipole-dipole forces. Dipole-dipole forces, or dipole-dipole forces in general, happen because we have molecules with polar regions. All right, let's do SH2. No, H2S actually. So, it's a very polar molecule. It's not going to be classified as an H bond yet. We'll discuss on why in a second, but we know it's a polar molecule. Sulfur, somewhere in the middle. Hydrogen, hydrogen, looks exactly the same as water, except I've got sulfur instead of oxygen. This is a polar molecule. The hydrogen sides, we already know, are going to be positive, and let's do positive in blue. We're going to do everything that's negative in red. So these sides are going to be positive, and then the sulfur is going to have a partial negative. So I can represent that as just a circle of space with one side being partially negative, the other side being partially positive, like something like that. Obviously not exactly the same, but just something like that. If I put another H2S molecule right next to it, what's going to happen? Given the proper orientation, remember, it already had a pre-existing charge. Let's say it was set up in this way. There are going to be attractive forces between that negative side of one H2S molecule and the hydrogens of the other one, and the hydrogens of that other H2S molecule and the sulfurs of the other one. These forces are IMFs. They exist outside of molecules always, and they happen under different circumstances. For the circumstance that we're talking about dipole-dipoles, it is a case such that the molecule was already polar beforehand, which means that most of the time, if you were to freeze this thing and look at the number of electrons, you're going to find them around sulfur as opposed to hydrogen, because sulfur has a higher electronegativity. Now, what about hydrogen bonds? A hydrogen bond, if we were to draw this arrow a bit more appropriately, it would be more so a subclass of dipole-dipoles. They're exactly the same thing, with one small exception. Hydrogen bonds, for starters, need hydrogen. And they require the three most electronegative elements in the periodic table. Either nitrogen, oxygen, or fluorine. If you have any of these three, you have made a hydrogen bond, and you also need hydrogen on the other side. Now, in this picture, in this little schematic, where does the actual H bond lie? Is it this? No. A hydrogen bond is not a classical bond. The hydrogen bond actually hasn't even been depicted in this case yet. So the ability to express these hydrogen bonds would need another molecule alongside it. The hydrogen bond would be this interactive force. We know hydrogens are always partially positive, and these three are very electronegative, so they're going to be partially negative. The hydrogen bond is this force. It's an IMF that connects, that brings together that fluorine side and the hydrogen side. Remember, no transfer of electrons, no sharing electrons, none of that kind of stuff. The only thing that happens is that there's an attractive force, Coulomb's law, you can analyze it that way too, between the negative side of one thing and the positive side of the other. So dipole-dipole, I have something that is polar, the negative side of one side attracts the positive side of the other. H bonds is a specific case of a dipole-dipole. And what of LDFs? LDFs follow the same idea, but it's a separate case altogether. An LDF is a temporary dipole. Temporary dipole or a temporarily induced dipole. Carbon-carbon atom. We know that carbon-carbon bond, we know they have similar electronegativities, right? It's a covalent bond. If we look at the region of space, we mentioned earlier how 50% of the time you're going to find the electrons in the center and roughly 10, 20, whatever, off to the sides. Point is, or 80% in the center. Most of the time, it's going to be in the center. But by pure chance, I froze this thing and I was somehow able to look exactly where the electrons are. I found out that it just so happened my two electrons were right off to one side. What has that done? By pure chance, this molecule now has a partial negative side near the electrons and a partial positive side away from them. If I put another carbon-carbon atom there, something with a carbon-carbon bond or anything that has just a normal covalent bond, it's not polar, this negative side is going to repel electrons. We know electrons repel, and remember, the reason they are there in the first place was completely by probability. We froze it, and it just so happened that at that exact moment in time, which is not something that's likely, but it can happen, we found them there. This negative charge is going to repel the other electrons, so now my electrons are going to want to migrate this way. This is the temporary dipole. This would be the temporarily induced dipole. It was induced by my other temporary dipole that happened by pure chance. So now there is a swap in the sides that are negative and positive. And these interactions can happen over and over and over and over and over again. LDFs are the weakest of these three IMFs. Dipole-dipoles in the middle, hydrogen bonds are the strongest. These two depend on whether a molecule has the capacity to actually create that bond. LDFs has a bit more than that. An LDF and the strength of the LDF will increase with molar mass. But that's just an indicator. That doesn't define why this happens. Why is it that something with more molar mass would be able to do this more frequently? The actual reasoning behind that is because it has a more polarizable, so the ability to have these interactions happen, electron cloud. An electron cloud is this region of space that we've been depicting this whole time. So the sum of all these temporary forces, all these induced forces that happen by pure probability, and then it was a domino effect after that, are known as LDFs, or London dispersion forces. On its own, it's very, very weak. But when you sum a ton of them, it's no longer negligible. It matters. Anything that has mass has electrons. And if you have electrons, you have the capacity to produce LDFs. And again, the reason being why something with an increase in molar mass has stronger LDFs is because it has a more polarizable electron cloud. So, what do IMFs even do? IMFs are going to determine a lot of material properties of any given molecule. First, let's talk about phase changes, boiling points and melting points and all this kind of stuff. You have seen a diagram that looks as follows. In the x-axis, we're going to have heat or energy flow, energy added, same thing. And on the y, we are going to have temperature. So imagine we're looking at water for a second. So what does this tell you? I added more energy and my temperature increased. Sure, that makes sense. Then all of a sudden I plateaued, which I added more energy and the temperature doesn't increase. It's a little bit weird. Then I added more energy, okay, again, increase, and then the same thing. Then from there on, you add energy and just continues to increase the temperature. What's happening? This is where IMFs start to come into play. Each of these flat regions represents a phase change. At this point in time, when we have very, very low temperatures, we are in the solid phase. This middle section is going to be a phase change from solid to liquid. Why do we experience phase changes and why is there no increase in temperature in a phase change? During a phase change, all of the energy added is going towards significantly weakening the IMFs present instead of increasing the temperature of the system. So rather than making my ice more warm, it is going into turning the ice physically from ice into water. Then the next region of space, once that whole thing has become water, we can start to go on to the next phase where we go from a liquid, water, to gas. And again, we're going to experience significant reductions in IMFs present. Then at the end, that last section just corresponds to the gas. When you go from a solid to a liquid, that's the melting point. Vaporization point would be liquid to gas. When you go from a solid to a liquid, my IMFs will weaken. When you go from a liquid to a gas, under ideal conditions, they effectively become zero. And what's the actual difference between these three things? How can we more accurately describe what a solid means, what a liquid means, and what a gas means? Let's picture three containers. Here, I'm going to put a solid, so ice. Solid water is going to have a crystallized structure. These little arrows I'm drawing, the little lines are not bonds, by the way. They're just a crystallized way of drawing the IMFs effectively. So every circle represents a little water. They are compact, they are fixed, and they cannot move. They can only vibrate. That would be a solid. Here would be a liquid, and here will be a gas. What happens with the other three? So here I weaken IMFs a decent amount. Now my water has the ability to flow. Having the ability to flow is called a fluid. Liquids and gases are both classified as fluids because the independent water molecules have gained the ability to flow. Then when you are in the gaseous state, there are no volume restrictions. Your molecules will go all over the place. They occupy a certain volume based on, well, we'll talk about gases a bit more later on, but they won't necessarily take the shape of the container. They'll expand, they'll either fit the whole container or they'll just expand up to a certain point. Water, on the other hand, is always going to settle at the bottom and take that definite shape of the container. But both liquids and gases have the ability to flow. So, if we were to increase the strength of IMFs, how could this curve change? One thing that could happen would be, here we know we're more dealing with temperature. and specific heat and all that kind of stuff. We'll talk about specific heat a bit more in thermochemistry, but let's analyze the flat part of the curve. If I increased my strength of IMFs, you can expect it to remain in that stage for longer. So rather than this only going through that section, it might be there for longer. Then we have the liquid phase. And then again, it will require more energy to break those IMFs present before going into the gaseous phase. So an increase in IMF strength would either increase your boiling point or increase the melting point, or require you to spend more time in that space. So it could either longen this horizontal line or increase it vertically as well. You will experience this at a higher temperature, and at a higher boiling point depends directly on the temperature, right? So first, IMFs are going to affect various things. They affect boiling points. An increase in IMF strength results in an increase in the boiling point. They affect the melting point. Increase in IMF strength results in an increase in the melting point. And point of condensation, point of etc., 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 all those phase changes. And then there's one that's different. Vapor pressure. So an increase in IMFs, here causes an increase, here causes an increase, here causes a decrease. Why is that the case? For starters, what is vapor pressure? You have a container. There's a bunch of water in it. Some of this water is going to have enough energy to escape into the gaseous phase. It's moving around here. This amount of water that has enough energy to become a gas is known as vapor pressure. So it's actually independent of temperature. An increase in temperature, yes, it will make a more vapor pressure, but vapor pressure doesn't depend on changes in temperature. It is that inherent quality of what's my pressure going to be at that point in time. How can you roughly see this? We can see this with something called Maxwell Boltzmann diagrams. That's the diagram that looks like this. What does this represent? Here we can have velocity or temperature. Things that move faster have to have a higher temperature, right? Kinetic energy 1/2 mv squared. And here a number of molecules. Going this way results in an increase in energy. So if this was a given sample of water, let's say water at 50 degrees, 20 degrees Celsius, some of this water is going to have enough energy to increase and go into that next phase. It'll be a small amount, but some of it will. Once we pass that barrier of energy, these molecules will be the ones that can escape into a gas, and that is what will cause your vapor pressure. So Maxwell Boltzmann and all this stuff with kinetic energy. Let's define kinetic energy again. Kinetic energy we know is 1/2 mv squared. Get rid of that 1/2 entirely. It's not going to affect anything in this class. And just make a proportionality constant with mv squared. Now, increase in velocity, increase kinetic energy, and an increase in mass, increase kinetic energy as well. The increase with velocity is to the second power. So it's more sensitive to fluctuations in velocity than that of mass. And in terms of our analysis, this mass isn't the number of grams, but really the molar mass of any given molecule. You always use Maxwell Boltzmann diagrams when we're talking about this to reference changes and see the kinds of things that you can see, what kinds of questions you're going to be asked. So again, here we had the number of molecules, and on the x-axis you are going to have either temperature or velocity. The reason I'm going to write velocity is because you can get more questions when you write velocity. Remember, energy, my bad. You can get more questions when you write velocity here as opposed to writing energy. If you put energy, you can't do any real like temperature questions and and such, it becomes a bit more confusing. Or if you put temperature here, obviously you can't get any temperature questions. So, velocity. If we have a sample of neon, so a bunch of neon gas, let's do neon at 50 degrees Celsius, at 25, and then at 100. This is going to be our standard bell curve for neon at 50 degrees Celsius. As we change the temperature, this has to change. You can expect a change in temperature increases your kinetic energy, so it should increase my velocity, right? But how do we reflect that in this graph? I'm going to make the 25 degrees case orange, and this case is going to be green. So an increase in temperature. What needs to be conserved is the total number of molecules. By adding energy to the system, I have an increase in number of molecules. So this area under the curve needs to be the same regardless of what we do. But we also understand that we have to express an increase in velocity with an increase in temperature. So by going to the right, the curve has to come down as well. An increase in temperature would look as follows, where more molecules now have a higher average velocity. What about the case where I decrease my temperature? When you are going to the left, you have to go up as well, because we are conserving the total number of molecules. So I have a slower velocity, but we're doing this to make sure that, again, that area under the curve is the same as it has been before. Increase your temperature goes to right and down, decrease temperature goes to left and up. The other kind of question you can get with this deals with changing the actual molecule. Let's compare neon, helium, and argon at 50 degrees Celsius. So again, velocity here, number of molecules here. If the graph that you're given is as such, how do we know who's who? Of these three molecules, who do you expect to move the fastest? Our measure for energy is going to be this temperature value. You know that temperature is directly proportional to kinetic energy. Not exactly the same thing, but they are very closely related to each other. Temperature is more a measure of average kinetic energy versus kinetic energy due to movement. Whoever has the highest temperature should have the highest kinetic energy, but temperature is the same. So what exactly are we changing? Kinetic energy is mass times velocity squared. Velocity is changing as a response to my mass. For this to be constant, if my mass goes up, my velocity has to decrease. If my mass goes down, my velocity needs to increase. So we're basically saying that given the same amount of energy, lighter things move faster and heavier things move slower, which is a completely intuitive idea. That being said, of these three, who is the lightest? Who has the smallest molar mass? Helium. At any constant temperature between the three, helium has to move the fastest. So this would be helium, and who's the heaviest? Argon. Argon would have to move the slowest. Argon's on here. And the center section would be for neon. And those are the two main kinds of questions you'll be asked with Maxwell Boltzmann in reference to this. There's a whole bunch of other stuff we can do with this, but we'll mention that more so when we're talking about thermo in the next couple videos. Now, gases. So we've mentioned gases, but there's one thing we haven't talked about yet. Every time the word gases comes out, immediately you need to think of PV equals nRT. This is the ideal gas law. There's a whole bunch of other sub-laws and different dependencies and whatnot. You don't need to remember anything. You just need to know any of them. You just need to know how to apply the ideal gas law. You can rearrange any of these terms to get whatever you want, and this gives you the dependency that you're looking for. If we're looking for the pressure volume dependency, you would be able to rewrite this as pressure is proportional to N times R times T over V. You don't care about that section, so we see that pressure and volume are inversely proportional. That's one of law, Charles' law, Boyle's law, or Gay-Lussac's, whatever you're talking about. I don't know. I don't remember exactly what they are. You don't need to. That's the point. This immediately tells you volume goes down, pressure has to go up, given the same number of moles, gas constant, which is always the same, and a fixed temperature. So what does ideal behavior mean? Ideal behavior can be summarized as the IMFs of any gases that we're looking at are approaching zero. Under ideal conditions, that should always be the case. Because of that, we're going to exhibit a number of properties. For starters, 1 mole of any gas at STP, standard temperature and pressure, will always occupy a volume of 22.4 liters. Always. Why is that the case? IMFs are zero, so there's no force bringing this whole thing together. And we have a constant standard temperature and pressure. It ends up being that if we look at a region of space and we have 1 mole of gases here, if you were to attempt to draw it in scale to the region, you would most certainly not be able to see one specific molecule. This little molecule that we drew is 1,000,000 times bigger than what it should be. There'd be tiny, tiny, tiny specks. The volume of all these tiny specks is insignificant in relation to the volume of the whole region that we're looking at. So if we're talking about argon versus helium, yes, the space argon takes up is bigger than that of helium, but it's insignificant in relation to the whole region. So we can approximate them all having a similar value of 22.4. Now, what else can happen? We have this idea of Dalton's law. Getting a bit cluttered, let's clear this. So what's Dalton's law? Dalton's law and his law of partial pressures says that the pressure of a system in total is going to be the sum of all the pressures in the system. These are going to come from different molecules, and they depend directly on the number of moles of that specific substance. If we have a container with 1 mole of H2, 1 mole of N2, these are all gases, and 2 moles of O2, given a volume of 5 liters, at STP, calculate the pressure. PV equals nRT. So my pressure would be equal to number of moles times R times T, divided by my volume. We know that I have 1 mole of helium, 1 mole of neon, and 2 moles of oxygen. Dalton's law tells you that the pressures are going to be directly dependent on the number of moles. 1 mole of helium, so the pressure of H2, in this case, is going to equal exactly the pressure of N2. Why is that the case? Because the moles of H2 are equal to the moles of N2. And you know the space that each of these were to take up if they would be unconfined is going to be 22.4 at STP, right? So you can calculate all the values using this. And effectively then, my total pressure would be the total number of moles, so 4 moles, times the gas constant times temperature divided by your volume, 5 liters. And from here, you can get the pressures in atmospheres or Pascal, depending on whatever units you use for that. The pressure of O2 is going to be twice the pressure of N2. Why is that the case? I have 2 moles of O2 compared to 1 mole of N2. You can do mole fractions which represent ratios of the total pressures from all this information. The mole fraction for H2 would be given by 1, the number of molecules, number of moles divided by 4. I have 1 mole of H2 and 4 moles of gas in total. For N2, it ends up being the same thing. Then for O2, it ends up being 102 over 4, so 1/2. That would be the corresponding percentage of pressure that it takes up. If you know the whole thing had a pressure of 5 atmospheres, then this would be 5 divided times 1 over 4. 5 times 1 over 4 and 5 times 1 over 2. That's the sum of Dalton's law. Now, a couple last topics before we wrap up this video. We've been talking a lot about ideal behavior, but we haven't mentioned anything with deviations from ideal behavior. How do deviations from ideal behavior occur? When the sum of your IMFs present in any gas does not approach 0. So it is some tangible number and it is physically pulling this whole thing apart together. Apologies. So obviously now 22.4 liters is no longer going to be the case, right, at STP. And a whole bunch of other stuff changes. How do we get those changes? Two things can happen. Either I have low temperatures or I have very high pressures. These two things are going to trigger deviations from ideal behavior. And why is that the case? Think about low temperatures. So I have molecules and they're moving slowly past each other, obviously a lot faster than water and gas and solids. Solids don't even move. But they're moving relatively slowly. You have a chance for intermolecular forces to form between all these molecules. That causes your IMFs to not approach 0. Instead, there's some tangible number. And in the case of high pressures, there's just so many molecules bound up next to each other because the pressure in that system is so high, your IMFs do have a chance to form, and it's not going to equal 0. Then the last topic to talk about is density. We can work with densities of gases, and there are some questions that if you haven't seen that kind of question before, it tends to be very, very tricky. So let's say we have given the following information. Let's try answer one of these questions. Imagine we have a gas. You are asked to find the molar mass of this gas. And you are going to be given the density of the gas. You will be given the temperature which the gas is at, and you will be given the pressure of the gas. So I have a ton of seemingly unsimilar ideas, and somehow you're supposed to be able to find molar mass from all this information. It is not intuitive at all if you haven't seen this kind of question, so I will just give you the answer. If you would like to try it on your own, go ahead and pause. But remember, when we're talking about gases, the first thing that should always come to your mind is PV equals nRT. So it's the first equation we're going to work with. Second thing, we're working with density, right? The whole thing, they gave us this density value, so somewhere along the way we have to be able to use it. Formula for density is density equals mass divided by volume. But how do we include molar mass in all this? Well, molar mass is the mass divided by the number of moles. So we have to find a way to rearrange this equation such that it solves for molar mass given all the stuff that we have. First thing to note, there's no volume here. The volume shows up right here and right here. So let's go ahead and rearrange this for volume. Volume is going to be nRT over P, and volume on this side is M over D. And you can set them equal to each other and get rid of that variable entirely. So nRT over P is equal to M over D. What else can we do? Right here we have M, and right here we have N. I'm going to move them off to one side and move everything else away from it. M over N, so I've divided by N, is going to equal, multiplied by D, dRT over P. And it just so happens that this quotient is your molar mass. So your molar mass will be given by dRT over P. we have the density, we have the temperature, we have P, and R is the gas constant. So given these three things, you can find molar mass. And with that, we'll wrap up this video. Thank you, everyone. I hope you have found this information useful. Please let me know in the comment section below if there's anything you'd like for me to change, if there's things that you think I did incorrectly, or just a style of video. This is my first time doing this side, along with the other video that I had just recently posted. I would like to continue doing this, especially if you guys find it helpful, and we do have a decent amount of material to cover. So I'll try to get this uploaded as soon as possible, and then let me know below in the comment section what you think. Thank you, everyone, and have a nice day.